Okay, good morning. So first quickly we will discuss the solution to quiz questions, and after that we will go to our new topic. Okay, so I am opening over here the questions. The first question is, draw the pH diagram for a reverse Carnot cycle that includes two compressors, one isentropic and one isothermal. So if you recall, when I was discussing the when I was discussing particularly the, so this is question number one. When I was discussing the vapor compression cycles, in vapor compression cycles, I told that if this is my TS cycle, reverse Carnot cycle on TS diagram will be something like this. Okay, so this is the standard cycle. Now, if because we don't have any device which can compress both liquid and vapor, so what I can do, I can extend up to saturated vapor point, and from there I can do compression up to the condenser temperature. So from 1 dash to 2 dash, and then 2 dash I can move in a constant temperature fashion. So of course 1 to 2 dash process is simply possible. It's nothing but isentropic compression. Okay, it's isentropic compression. But what about process 2 dash to 2? So if you see a constant pressure line which is passing through point 2, so that will be having say pressure P2. This is a constant pressure line, or maybe let me write it condenser pressure. I'll be having one constant pressure line over here with PE. Through point 2 dash, there will be some another constant pressure line which will be moving something like this, and this pressure is some intermediate pressure which is less than PC and greater than P. So over here you can see I have stopped at point 2 dash. Now from 2 dash to 2 I am changing pressure from PI pressure to PC pressure, and that I am doing in an isothermal fashion.
Sir, the intermediate pressure line will not go to the liquid saturated liquid.
Saturated, yes, of course it is there, but I am stopping at this point, no? Okay, from this point I am not following this line, I am following this line because I have to maintain constant temperature process, then only I'll be able to achieve the Carnot cycle. Okay, so 2 dash to 2 is 2 dash to 2 is the process in which temperature is constant but pressure is changing from PI to PC. So it's a isothermal compression process. Now same thing you have to, I have drawn it on the board as well. Now this you need to draw pH diagram. So pH diagram is very simple. Three pressures, PE, PI, PC. Okay. Now 1 to 2, sorry, 1 dash to 2 dash is this. Now 2 dash to 2 is which process? Constant temperature process. On a pH diagram, constant temperature line appears something like this. So it means this is constant temperature 2 dash to 2. Then 2 to 3 as usual. Now 3 to 4 will be isentropic. So because of isentropic it has to go like this. It should not be perfectly straight. Those who have not drawn it isentropic but they have correctly drawn the right hand side, that I have given marks. Okay, because right hand side was more important. Is this one clear? So it should be, this should be your pH diagram. Only two people have drawn it. That two, 3 to 4 all have joined straight line. Question number 2. Which one of the practical limitations is avoided upon the use of liquid subcooler in a vapor compression refrigeration system? Very simple answer. Why we do subcooling? What was the limitation of flash chamber? which we avoided in subcooling. So if saturated liquid enters, comes out of the flash chamber, then there will be chances that before the inlet to the expander, there is small amount of vapor formation. However, the expansion device is designed only for pure liquid operation. If some amount of vapor goes, it will lead to sluggish operation, or there will be malfunction and flow can completely stop. So because of which, to ensure that there should not be any vapor formation at the entry of expansion device, we do significant subcooling. Okay, is this one clear? Next is one key advantage of closed air refrigeration cycle over open air refrigeration cycle. Very simple. The very first key advantage is that in a closed cycle we can operate at high pressures. If we operate at high pressures, then the density of working fluid will be more. Okay, if density is more, for achieving same mass flow rate, volumetric flow rate handled by the components will be less. Therefore, the size of the components will be. This is one of the major advantage. If you just go in an open cycle, you have to take air from atmosphere, you have to dump air into the atmosphere. Okay, so corresponding to atmospheric conditions, pressure conditions, your density is very low. But if you operate in a closed cycle, instead of operating your heat rejection process at very low pressure, you can operate it at any higher pressure than the atmospheric pressure. So their density will be more. Volumetric flow rate handled by each component will be less. So size of the system will be less. You can have the same pressure limits. Instead of air, you can use other gases also in a closed cycle. You need not to use air only. Yes. Sorry? That will be not always true. That will be depending upon operating parameters. It will depend upon operating conditions, not on this. Why is two-stage compression performed in a bootstrap air conditioning cycle? Please tell me. I have explained this point. I told you that whenever we go at high Mach numbers, then the ram pressure P2, it becomes large. If ram pressure becomes large, then the corresponding temperature is also large, and whenever you do the cooling using the ram air, that does not come to very low temperature. Okay, so if it does not come to low temperature, then there are two possibilities: either to use some external medium which can decrease the temperature, or increase the pressure to higher value so that expansion takes place in the turbine across large pressure ratio. Okay, if expansion takes place across large pressure ratio, then we will be having actually low temperatures at the exit. Shall I explain this? Shall I explain? What was the TS diagram? 1 to 2, then 2 to 3. Okay. And then we were doing cooling. Okay. And this cooling, generally 3 dash to 3 cooling is done with the help of air which is at temperature T2 dash. Okay, this is used for cooling. After this point, we do the expansion in the turbine and then we supply air to cabin. Okay. Now the simple point is, at high Mach numbers what happens? This value increases. T2 dash increases. Okay. So instead of this, it may go up to this point. So if it increases, then further if you are going only up to this pressure, then if you do cooling, you can only come up to this point. Okay, in a simple cycle, the cooling could have, in an ideal condition, cooling could have come up to this point. But in increased scenario, cooling can come up to only this point. Okay. Now, from this point, if you do expansion, then your initial temperature is, pressure ratio is same, but initial temperature is higher than this. So corresponding final temperature at the exit of expansion process will also be high. So there are two ways to improve. Either keep the same temperature, increase the pressure, or keep the same pressure but decrease the temperature. So there are two things. In case of bootstrap cycle, what we do? After initial cooling, further we increase the pressure. Again we do compression and then we again do cooling, so that even if I am at same temperature, my inlet temperature is same, but expansion will be done across large pressure ratio. Okay, so that because of the large pressure ratio, I can have less value of temperature at the exit of the. This I have explained you while discussing about the bootstrap cycle. Okay. And what we do in case of regeneration? In case of regeneration, we don't do this compression, but we were coming up to this point spontaneously. After that, whatever the exit air is coming at the exit of turbine, partly that air only we use for further cooling. So we do expansion across the same pressure ratio, but we do cooling by using the chilled air only, which is coming at dark temperature. Okay. Revisit bootstrap and regeneration cycles. Is this point clear? Why we do two-stage compression? How low dart is achieved? Same, again I answered. How low dart is achieved in a regenerative aircraft air conditioning cycle at high Mach number? So what we do in regeneration cycle? We don't do two-stage compression, but after doing spontaneous cooling, we use the some fraction of chilled air which is coming at the exit of turbine. Again we circulate it to cool the air further to low temperature before coming to the entry of turbine. Is this point clear? Clear or not? What will be the value of superheating horn area for a refrigerant with a positive slope on saturated vapor line on the TS diagram? So, what is the meaning of positive slope? TS diagram, yes, so TS, dt by ds is slope. So I have to draw the TS diagram in such a way now. Is this slope positive? Even something like this. Is this slope positive? You see, this is a positive slope. Okay. Now if I compress from point 1, what will be happening? Compression process will move along this and I will be having either very minimal or no superheating. Okay, this is also drawn while discussing the lectures. And mostly people have done this. Is this point here? So superheating horn area will be almost 0. So there is no superheating horn in this case. Represent the specific work saving, specific work It means work per unit mass. Specific work saving achieved in multi-stage compression upon using intercooling on the TS diagram. How to represent compression process on TS diagram? How one can represent compression process on TS diagram? Compression process is an isentropic process. Okay, so if I am starting from point 1, it will be 1 to 2 compression. Then I will be having intercooling. What will happen in intercooling? Temperature will decrease. What I have written TS only na in question. TS. Okay. So what is 1 to 2? 1 to 2 is a, please tell me, isentropic process. It will be like this. Okay, and after that, what we are doing? We are doing, is this isentropic process? Correct? Yes. No, no. After that, we are doing, what we are doing? Please tell me. Let me use the dome. This is process 1 to 2. Okay. Then at point 2, what I am doing? Intercooling. Okay. Intercooling, so it means isobaric heat rejection. Okay. At constant pressure, we are doing intercooling. So how process will be looking like? Like this. So 2 to 3 will be intercooling. Then from point 3 again I will be doing the isoentropic compression. So I will be going to point 4. If I don't use intercooling, then this 2 point would have directly extended to higher pressure at point 2 dash. So it means intercooling led to savings in this much amount of work. This you have to represent. That was the question. Understood? 1 to 2, then 2 to 3 is intercooling, 3 to 4 is compression. If I don't use this intercooling, then from 2 to 2 dash line will be extending like this up to the high pressure, and this additional area is actually the work which we had to spend. So because of intercooling, this is the specific work saving. Is this point clear? Anyone is having any doubt about this? Please tell me. Okay, mention the need for the use of cascade refrigeration system over a multi-stage compression system. Please tell me, quickly tell me, what is the need for cascade system?
Higher temperature and produce higher temperature difference.
So I told you simple thing. Whenever we are using multi-stage system, we maximum go up to 3 stages of compression. Okay, because if we go more than 3 stages, then the thermodynamically it is feasible, but first point is capital cost increases, and second important point is there are some practical limitations. What is the practical limitation? For example, a working fluid, I am using some high pressure working fluid. I have explained you two types of working fluids. High pressure working fluid, it means its boiling point is, what is the meaning of, yes, towards the higher pressures. Okay, so in that case what will be happening? Whenever we will be operating it to very low temperature conditions, corresponding to that its pressure has to be maintained less than the ambient pressure. There will be leakage. Other important issue is, if pressure is very low, then specific volume is very high. Okay, if your specific volume is very high, then volumetric flow rate, which is to be handled by the compressor and evaporator, that becomes very, very large. Okay, so because of that, we go for cascade refrigeration system. Is this one clear? Simple one-liner answer for every question. Then next is derive an expression for increase in pressure due to the ram effect in an aircraft and mention the necessary assumptions. Assumptions probably not correctly mentioned and very few people mentioned. I think in class I have derived for the temperature, which people have derived as it is, and after temperature we need not to use the, because the RAM process is a reversible adiabatic process. So we could have simply used pressure temperature relation for reversible adiabatic process, and that would have simply given the pressure ratio. So P2 by P1.
We will get ideal.
Yes, yes, yes.
After that, we have to get period also using efficiency. We have to get period like real pressure.
No, simply P2 by P1 is equal to T2 by T1 gamma minus 1 by gamma. Okay, so if I apply between the, what is entry of RAM? 1 point, exit of RAM is 0.2, and process is reversible adiabatic. So it means that P2 by P1 is equal to T2 by T1 gamma minus 1 by gamma. Okay, so that step also people have not done. So point is, please start practicing. Unless or until you practice, you are just listening in the class and after that forgetting everything, it will not work. Okay, so do practice. I have already given you the assignment. Practice numerical problems from assignment as well, because exams are starting from 22nd only. Okay, so you have to practice actually. Okay, let us now did the schedule for exams announce?
I see the 23rd to first slot.
23rd?
First slot.
RAC is first slot. Okay.
The second slot.
But you people will be having some other exam on the second slot. They are ready. Okay, so let us now discuss the next unit. It's vapor absorption refrigeration system. And in short form, you can call it VARS. Okay, so earlier we were talking about vapor compression refrigeration system. Now we will be talking about vapor absorption refrigeration system. Before going into the exact details of the vapor absorption refrigeration system, let us first discuss about the fundamental concept which we will be utilizing over here. Okay, so let us consider I have two chambers. This is my one chamber. There is a valve between the two chambers, and this is another chamber. Now in the first chamber I have ammonia. NH3, and in the second chamber I have water. Okay, let us consider at the ambient condition both are having temperature of 30 degrees Celsius. Okay, now out of ammonia and water, which one is having higher boiling point at atmospheric pressure? Water. Okay, water is having higher boiling point at atmospheric pressure. It means that if both are maintained at 30 degrees Celsius, then if the pressure inside the ammonia chamber is P1, pressure inside the water chamber is P2. If both the temperatures are same, the corresponding saturation temperature will be, corresponding saturation pressure will be higher for ammonia in comparison to that for water. Is this point clear? All are clear with this point or not? Okay. So if you can go to property tables of ammonia and water, at 30 degrees Celsius for water you will be finding some value of saturation pressure, and at same 30 degrees Celsius you will be finding some value of saturation pressure for ammonia, and the saturation pressure for ammonia will be more in comparison to saturation pressure for water. Okay, usually because this majorly comes because of the intermolecular interactions between ammonia molecules and water molecules. Okay, so water molecules are ammonia molecules can, vapor molecules of ammonia can more easily escape, and ammonia can result in more vapor formation at the same temperature condition. Okay, so P1 will be greater than P2. Now let me do one thing. Let me open this valve. If I open this valve, what will happen? Ammonia vapor will start transferring from this chamber to this chamber. Okay, from high pressure side to low pressure side. So whenever ammonia vapor will start transferring from this side to this side, because ammonia has to maintain its pressure, so there will be more and more vapor formation in the ammonia chamber. So if more vapor is forming in the ammonia chamber, it means evaporation is taking place in the ammonia chamber. So the remaining portion of the liquid will start cooling. Is this point clear? All are clear with this point or not? So remaining, in the remaining portion, because more and more ammonia vapor is forming, so this liquid, basically whatever ammonia vapor is forming, it is taking the latent heat of vaporization from the remaining vapor. So this is called evaporation process, and we always know that evaporation causes cooling because it takes the latent heat of vaporization. So that's why it will be actually its temperature will start decreasing. But if its temperature decreases and this vapor just keep on depositing over here, then after some time this pressure will be becoming same and the process will stop. But if we see the properties of ammonia and water, water is having good tendency for solubility of ammonia. So it means ammonia solution can easily mix in the water. Is this point clear? So what will be happening? Whatever the ammonia vapors are coming over here, these ammonia vapors will be condensing in the chamber, and these will mix with the water to form a mixture of ammonia plus water. Is this point clear? So I will be finding in this chamber, now I will be having a liquid mixture of ammonia plus water. So how ammonia is coming? Basically ammonia vapor has come, and that ammonia vapor has, what happened? Condensed. Okay, so when ammonia vapor has condensed, these will be releasing latent heat of vaporization. So temperature of this mixture should increase. Okay, so temperature of this mixture should increase. We will allow this to happen so that, say my temperature over here is reaching to some temperature of 5 degrees Celsius. Now after some time temperature inside this is say 5 degrees Celsius, and temperature over here is say 40 degrees Celsius. If you don't stop this, then this temperature will keep on increasing, and finally its pressure will also keep on increasing, and the process will ultimately stop. But if I use a cooling water coil over here, so that whatever is the heat released by ammonia vapor, that heat I can simultaneously take it out. Then what will happen? This temperature will remain only at 40 degree Celsius. Now, if this liquid has reached at 5 degree Celsius, and after that I have put this inside my refrigerated space, which is to be maintained at say temperature of 10 degrees Celsius, then what will happen? This refrigerated space will also start transferring heat to the first chamber. Is this point clear? So here this first chamber will act as a evaporator and second chamber will kind of act as a condenser. Is this point clear? This will act as a condenser. Now there are two possibilities for stopping this operation. First possibility is that in this water vapor now, the ammonia mixture concentration has increased and it has reached to some point after which the water cannot hold more amount of ammonia. Okay, after that what will happen? Whatever ammonia vapor will come, that will just keep on presenting at the top. Is this one clear? Second possibility is that my entire amount of ammonia, liquid ammonia, has evaporated in the first chamber. Is this point clear? When any of these two conditions have happened, my refrigeration process will stop. So what I need to do now? In order to again do the refrigeration, I have to again go back to the original state. Is this one clear? Again I have to go back to the original state. So in order to go back to original state, what I'll do, I'll use these in open position only. So this chamber was not having any ammonia and this chamber was now very much filled with ammonia and water. What I'll do now? Now I will start heating this first chamber. So if I heat the first chamber in a mixture of ammonia and water liquid, which one will vaporize first? Ammonia is having low boiling point, so ammonia will vaporize first. So now ammonia vapor will rise from the top if I add heat to this mixture, and ultimately at the bottom I will be left with water rich mixture. Okay, so which will be having very low concentration of ammonia and most of the water will be present. And all these ammonia vapors which are coming over here, in order to convert these to liquid state, I need to cool this. So here I need to further do cooling so that my vapor of ammonia can convert into liquid. So if I do this operation, then again I can come back to the original situation. Okay. Is this point clear? So it means if I simply take two chambers with water and ammonia, I can do refrigeration. But for achieving but that refrigeration, whatever I will be doing, it will be an intermittent refrigeration. Okay, in part of the cycle I can do refrigeration, then I have to stop, reverse the process. For that I have to spend some amount of heat in the generator and some amount of cooling I have to do in the first one. Okay. So if now I have to operate this entire process in a cycle, how we can do this? Can you get some idea how we can do this? Let me draw the schematic diagram of a vapor compression system. In vapor compression system, I have a condenser, then I have expansion device, then I have evaporator, and after that I have a compressor. This is the vapor compression system. If I see in this vapor compression refrigeration system, which component is the most energy consuming component? Compressor. Okay, so compressor is the one which consumes most of the energy. Why? Because we know that work done for an open system is minus integral of VDP, and at the inlet of compressor over here I am having specific volume of vapor, and specific volume of vapor is very large in comparison to specific volume of liquid. That's why it will be consuming huge amount of work. But if I can operate this cycle in such a way so that I am replacing this compressor with some other arrangement which can actually give me the same pressure ratio, okay, with the help of which I can achieve the same pressure ratio, but instead of liquid, instead of vapor, if I can make liquid over here, okay, then I will be able to save significant amount of work. Okay, so let's see this how we can do now. So this is my VCRS. Now we will talk about another cycle which we call as VARS system. So in VARS system I will be having condenser. After condenser, expansion valve. After expansion valve, evaporator. Any movie is going on? So then after the evaporator, what I will be having? Now I will be using a chamber in which what I have? This is water plus ammonia, and here I will be having pure ammonia vapor. So whatever the pure ammonia vapor is coming, instead of passing this pure ammonia vapor to compressor, I am passing this through a solution of water and ammonia. Okay, so what will happen in this solution of water and ammonia? Or let me connect it from the top. Likewise I am connecting. So vapor is entering into this, and along with that I am using a cooling coil over here, which is taking heat at some amount QA. Okay, at the rate of QA, it is rejecting heat from this chamber. So what will happen now? Continuously this vapor will keep on flowing and this vapor will keep on condensing. After condensation it will form a mixture, and this mixture will be having rich concentration of ammonia. Now what we need to do? After some time this mixture will stop its functioning, because if say significant amount of ammonia has mixed in this, then it will be saturated. So what we need to do, we need to again make it as a weak ammonia solution so that it can hold more amount of ammonia. So for that purpose what I will do, whatever the mixture of ammonia and water is forming, this mixture I will pump. Now I will pump this mixture to some higher pressure inside another chamber. Okay, so this was entering at evaporator pressure. Now I will pump this up to the some other chamber which is maintained at pressure close to condenser pressure. Again I am doing the pumping process, changing pressure from PE to PC. DP is same, but now what I am pumping? Liquid, and the specific volume of the liquid is of the order of 10 to power minus 3 meter cube per kg. So the amount of work which you will be spending on this pumping operation, that will be negligible in comparison to the amount of work which we have spent in the compression process. Is this point clear? All are clear with this point? Because it is almost 1000 times greater in comparison to this one. Is this one clear? Now what I need to do? Please tell me. Here though I have increased the pressure, but here again I am having mixture of ammonia and water. But in the condenser I need to send only ammonia. And whatever water will be forming over here, that I can pass to the bottom chamber. Okay. So here in order to separate out the solution of liquid solution of ammonia and water, what I need to do? I need to heat it. So I will be adding heat, Qg amount of heat over here. Okay. Upon addition of heat, I will be finding that ammonia vapor from the top will be escaping, which we can pass through condenser, and at the bottom I will be having water rich mixture which is having small amount of ammonia, and this water I will be taking out. When I have taken it out, its pressure is PC and bottom chamber is at pressure PE. So it means I need to use over here some pressure reduction valve to decrease the pressure to this condenser. Is this point clear? All are clear with this point or not? Anyone is having any doubt? One important thing which we need to consider over here is, you see here I have added Qg amount of heat to water. So temperature of water will be high. Say the temperature of water over here is Tg. But temperature here, our requirement is we should maintain low temperature. Say temperature over here is Ta. Okay. So this water is coming with Tg temperature and here I need to maintain Ta temperature. So if it at Tg temperature itself it mixes, then I need to remove more amount of Qa amount of heat to maintain this water temperature. So what I can do, and after the pump this liquid is mostly coming at Ta temperature over here and here it is to be heated up to Tg temperature. So what I can do, in between these two I can connect a heat exchanger. So I can call it as a preheater. In this preheater, this hot fluid can transfer some amount of heat to this cold fluid. So cold fluid will be preheated, which further we need to heat in the top chamber, and this will be cooled, which further we are cooling in the bottom chamber. Is this point clear? So we can use a preheating heat exchanger. The chamber which we are using at the bottom, this chamber is something which is called as absorber. Okay, it is called as absorber because what it is absorbing? It is absorbing ammonia vapor. The solution which we use inside this chamber, this solution is called as absorbent. So over here, water is being used as absorbent. For ammonia water system, water is being used as absorbent. Is this one clear? And the top chamber where we separate out water and ammonia. It means we are generating water also, we are generating ammonia also. So this chamber is called as generator. Is this one clear? This is called as generator, this is called as absorber, and in between we have a preheater. So the combination of absorber, pump, preheater, generator and pressure reduction valve, if I use 5 components simultaneously in place of compressor, it will be saving my whatever work input I am giving. Okay. However, if you see in terms of the heat input, the significant amount of heat input I need to supply in the generator so that I can separate out the water and ammonia. Okay. So, why this system is preferred? It is taking less work input, but it is taking good amount of heat input. Okay. Work is always a high grade energy. So our effort is always to reduce the high grade energy whenever it is being consumed. Okay. However, heat, which is a low grade energy, it is available in abundance. How? You can use a solar collector, solar thermal collector, with the help of which you can convert solar energy into heat, and that heat can easily be employed in the generator for segregation of ammonia and water. Whenever we operate in different industrial system, for example in thermal power plant, in the condenser, we are removing significant amount of heat. Okay. In a chemical plant, in a process industry, we may have significant amount of heat which is directly being dumped to the atmosphere. We can utilize that waste heat for operating my refrigeration sector. Is this point clear? Are you getting my point? So the advantage of vapor absorption system over the vapor compression refrigeration system is that it consumes least amount of high grade energy. It consumes very less, almost negligible amount of high grade energy which we are supplying as a pump work, and there it was the compressor work. But on contrary, it consumes good amount of energy, but that energy is a low grade energy, and that low grade energy we can provide from different sources. Okay. Now, if we have to analyze the performance of the system, so if I draw a control volume around the entire system, because it's a cyclic process, so what are the heat and work interactions? One is WP work interaction, pump work. Then here it is QE, heat coming to evaporator, QG, heat coming in the generator, and QA, which is heat going out of the actual. Okay, so it means as per first law of thermodynamics, I can write that QE, which is the heat entering to the system, plus QG, this is also heat entering to the system, minus QA, which is the heat we have rejected in the, plus WP is the pump work, is equal to 0. However, I can make one assumption over here that WP is negligible. Yes. Sorry, correct. Yes. So, in the condenser also, what you are doing? You are dumping the heat to the surrounding. So, minus of QC also you can include it. Generally, generator temperature will be larger in comparison to the condenser temperature. Okay. Is this one clear? So, here please remember this QC I missed, so QC will also come. If WP is negligible, from here I will get that QE plus QG is nothing but equal to QC plus QA. Okay, so QE and QG is the energy supplied, and QC and QA is the heat removed. If I have to define the COP of this cycle, what will be COP of this cycle? Refrigeration effect. What is refrigeration effect? QE. And in order to achieve that refrigeration effect, whatever the input I am giving, what input I am giving? QG plus WP. But WP is negligible, so it means only input I am giving QG. So this should be COP of the cycle, QE divided by QG. All are clear with this? Now, from the second law of thermodynamics, what we need to do? We need to now determine what could be the limiting value of the COP for this situation. So how we define limiting value of COP? Always we consider the most ideal situation. Most ideal situation is all the processes are totally reversible. Okay. So if we go with that, then we know that as per the Clausius inequality, cyclic integral of del Q by T has to be less than equal to 0. However, for a totally reversible system, it will be equal to 0. It will be simply equal to 0. Now you write down, if QE amount of heat I am rejecting, I am adding to the system, then QE, and usually QE is added at TE temperature for a totally reversible system. So QE by TE is coming to the system, plus QG by TG is also coming to the system. What is going out? Minus QC by TC and minus QA by TC. It is also TC. Why? Because in the condenser I am rejecting heat to the ambient. In the absorber also I am using only the ambient water to cool the solution. So it means both are rejecting the heat to the ambient. Otherwise, if for this absorber, if I use some other chilled water system, then some energy has to be invested over there as well. Okay, but that we are not considering in analysis. It means the ambient water is being used for cooling the absorber. Okay, so this has to be equal to 0. From here I will be getting that QE by TE plus QG by TG equal to QC plus QA by TC, and QC plus QA I can replace with QE plus QG from the previous energy balance. Okay, so I can write it as QE plus QG by TC. Now take out QE common on each side. So what I will be getting, or maybe let me write it less than equal to 0 because I am going for a limiting case. So let's go with inequality. Okay, so what I will be getting over here, QE will be common 1 by TE minus, or let me take it other way, yeah, fine, 1 by TE minus 1 by TC is less than equal to QG, and here I will be getting 1 by what I will get out of this, QE into TC minus TE divided by TETC is less than equal to QG into TG minus TC divided by TC TC will cancel out. Okay, and I can get that QE divided by QG will be less than equal to TG minus TC divided by TG into TE divided by, is it correct? Sorry? Anything wrong? Okay, so QC plus QA I have replaced with QE plus QG, which is from the equation 1. Okay. Okay, so what is QE by QG?
COP.
So it means maximum limiting COP. Here you see this is less than equal to sign. So it means this is the maximum COP. Actual will be less than this. So maximum limiting COP is TE by TC minus TE. What is TE by TE minus TC? COP of reverse Carnot refrigeration when it is used in a VCRS mode, vapor compression refrigeration system. And TG minus TE divided by TG, it is nothing but the efficiency of a reverse Carnot, efficiency of a Carnot heat engine. Efficiency of a Carnot heat engine. Now you can see the maximum value of COP of absorption system is COP of vapor compression refrigeration system multiplied by efficiency of the heat engine. Efficiency of heat engine will always be less than 1. What it means? It simply means COP of VARS will be always less than COP of, even for Carnot cycle, this efficiency cannot be 100%. Okay, there has to be some amount of heat to be rejected as per the Kelvin-Planck statement of second law of thermodynamics. Is this one clear? So that's why if a factor with less than 1 when it is multiplied with this. So it means COP of vapor absorption system will always be less in comparison to. But still, with less COP, we want to operate it because whatever the energy we will be utilizing, it will be waste heat or low grade energy, okay, which will be leading to less operating cost. So you can see simply, I have three temperature limits. One is TG, other is TC, and one is TE. So it is like I am operating a heat engine in between TG and TC, which is doing W amount of work by taking QG heat and removing QC. And then here I am using a refrigerator which is using this work, and then it is removing heat and taking QE amount of heat. So that is the same thing, na? Because TE, here you have TE by TC minus TE, which is VCRA system, refrigerating system, and this is a heat engine system. Okay, so vapor absorption system, this is about the efficiency of the system. Now, understanding of vapor absorption system, if we have to do the real practical cases, how we can determine the properties of working fluid, we have to know something additional, because what is happening over here, we do not have the single homogeneous substance. How many substances we have? We have a mixture of two substances. So once we have a mixture of two substances, we first know the understanding of mixture laws, how mixture laws function, and then how the mixture properties will be changing with different parameters, that we have to actually know. Okay, so that we will discuss in the next class.